Good morning, everyone. Can I start? Sure. Okay. So, good morning, everyone. I'm Ajay, and this is Sanjit. And today we'd like to talk a little bit about artificial intelligence and deep learning. So, a little bit of background information. Both of us are students of HLC International School, and we are currently in 11th grade. We will mostly do deep learning and AI projects for fun, and we'd like to share our experiences as well as a little bit of information on what exactly AI is and the state of things today. So artificial intelligence is a very hyped topic right now, but honestly, cutting through the hype, there is pretty much a very specific set of tasks that AI is meant to solve. So this is just a broad overview to make sure we're all on the same page. Artificial intelligence is sort of like this broader category. We'll slowly come to define these terms a little later on in the talk. But within artificial intelligence, we have this field called machine learning, which is essentially using data and running algorithms to run inference and predictive models on this data. And there's also a very specific set of algorithms within this field of machine learning called the neural network. And the neural network has seen tremendous improvements in performance in the recent years, and has pretty much created this new field called deep learning. And the name deep learning comes from the fact that you're using deep neural networks.
Okay, so most people think that they know AI, but before we can really understand and appreciate AI, we need to know the difference between automation and AI. So automation can be defined as the technology by which a process or procedure is performed without human assistance. In the case of automation, it is if X, then Y. But when it comes to AI, it is intelligence demonstrated by machines. Its main ability is it can mimic what a human does or thinks. And popular example would be the maze. When you give a maze to an automated machine, you usually instruct or feed the solution to it, and this will enable the automated machine to solve the same maze over and over again n number of times. But when you give it a new maze, it will use the same solution given to it for the previous maze, and it will not really solve the new maze, it just follows the instructions given to it. But when in an AI system, if you feed it one solution, it will think from then on and solve multiple different mazes, and over again and again. It can keep going, it can keep doing it forever. With the introduction of AI, different types of learning have been made easier. The most important or popular being supervised learning. Simply put, for example, you have a 5-year-old kid who wants to know the difference between a cat and a dog. So in order for you to train the kid, you take 500 images of cats and dogs, and for every image you go, this is a cat and this is a dog. Simple as that. So after you train the kid will start to think on its own, and he'll be able to identify what a cat is and what a dog is. Next is unsupervised learning. Unsupervised learning is if you take the same kid, put him in a room all by himself and those 500 images. After a point of time, once he goes through those 500 images, he starts to figure out a pattern between cats and dogs. Then he starts to categorize and cluster them into pool A and pool B. He may not necessarily know that pool A is cats and pool B is dogs, but he will be able to identify similar trends in images. So next is reinforcement learning. This is when you take an AI agent and put it in an environment and you give it an objective. In this case, it's a lunar rover, and its objective is to land the lunar rover between those two flagpoles. And it learns from its failures. Basically, what it does, it tries over and over again, and finally it figures out an optimal way to land the lunar rover between those two flagpoles using minimum fuel.
So for the rest of this talk, we're mostly going to be focusing on supervised learning, as this is where majority of the economical value lies today. Essentially, supervised learning is nothing more than learning A to B mappings. So for example, a very old machine learning algorithm is given an email A, can you classify it as spam or not spam? An A to B mapping. Another example would be when you're given a piece of audio and you're asked to transcribe it. This is also known as speech recognition, but in the end it's still an A to B mapping. You're mapping audio onto a text transcript. Another example would be machine translation, where you're given a series of English words or English sentences and asked to translate them into French. Again, an A to B mapping. But this very simple act of learning the mapping between A and B has provided immense value. So why do we need deep learning in the first place? Well, the algorithms which we're going to be talking about today, like neural networks, aren't actually quite new. They're over 20 years old. However, back in the day, we did not have enough processing power and enough data to make these algorithms run efficiently and deliver high performance. So if you take a look at some of the older machine learning, the traditional machine learning algorithms, there became a problem. As the IT revolution began and we started getting more and more data from all across the globe, the performance of these old machine learning algorithms did not scale as well with the amount of data. However, with deep learning, we now have a greater performance with larger data sets, which has allowed us to achieve incredible accuracy, sometimes even surpassing human level performance. Okay, so finally, deep neural networks. This is the main algorithm used in deep learning today. So we're not going to go too much into detail on how exactly a neural network works, but the idea is that this algorithm, which is represented by the diagram to your left, learns the mapping or learns the representation of complex data sets, and this algorithm, the neural network, has seen large improvements in recent years thanks to the advent of big data and GPUs. So the main differentiator between a deep learning algorithm and a machine learning algorithm would be the number of hidden layers. So hidden layers essentially is increasing the complexity of the algorithm to learn more complex features from data. So now we're going to discuss about another improvement in the traditional neural network architecture called convolutional neural networks. We don't need to go too much into the theory of convolutional neural networks, but the idea is that when we're trying to create a neural network that's able to analyze images, we need a new technique. So let's say we want to create a classifier to classify images as cats or dogs. So an intuitive approach would be to feed in the individual pixel values of an image into a neural network and to predict a class label. However, this turns out to be extremely computationally expensive, and it's also not how our human visual cortex works. When we see images, we don't see them as individual pixel values. We first see basic elementary data points like a vertical line or a horizontal line. Our brain then puts these together to form elementary shapes like squares, circles and triangles. The later layers of neurons in our brain actually then puts these elementary shapes together to form elementary features like an eye or a nose, etc. And finally we put these multiple eyes and noses together to identify that this is a person's face. And this is what we are essentially trying to recreate with convolutional neural networks. Of course, these convolutional neural networks need to be more formally defined. So this is a quick overview of how a convolutional neural network works. In particular, we're going to be focusing on the convolution operator. So we have our image over here, which is represented by this green matrix, and yeah, the representation of an image is a matrix. So we take a smaller matrix that's smaller than the image size. This matrix is called a filter, and we slide it over the larger image. So it's kind of like taking a flashlight and sliding it over your entire image, and at each step you're performing an element-wise multiplication of the entry in the filter matrix and in the image. We then sum all of these up together to create a new matrix called the convolved feature. This matrix holds some information on more complex features than individual pixel values. For example, this particular convolved feature might correspond to a vertical line in the image. So this sort of gives us a sense of how many vertical lines are present in the image.
TensorFlow is an open source deep learning framework used for numerical computation. It allows developers to quickly build and deploy deep learning models such as the neural networks.
So TensorFlow was created by Google, and it was open sourced in 2015, and since then it's had a rapid growing community. There's also a lot of online support over now. We'll now move on to actually implementing a convolutional neural network to identify handwritten digits, and we're going to do this not only using TensorFlow but using another important software stack called Power AI. Okay, so a little bit of background. So Power AI is a software stack that contains all the popular deep learning frameworks such as TensorFlow, and there are also a few other ones like Caffe, Theano, Chainer, etc. And Power AI essentially encapsulates all of these frameworks and optimizes them to run on IBM Power systems. So the example we have over here it's a Jupyter notebook, and yeah, it's a common TensorFlow example that we've pulled off of GitHub. And what we're doing over here is essentially training a convolutional neural network to identify handwritten digits. Some of you might be familiar with the MNIST data set. Yeah, we're essentially training a convolutional neural network on that. But this isn't any groundbreaking new architecture. What we wanted to demonstrate with this particular notebook is how efficient, fast and easy it is to get started running a deep learning algorithms on IBM's Power AI platform. Yeah, and as you can see, probably in the next bit over here, you can see how fast our algorithm is able to train. So the most computationally expensive and time demanding step of any deep learning process is the training step, where you're iteratively going over your data set and trying to learn from it. This step is done incredibly fast with IBM's Power AI system. And yeah, if we wait for a minute, we'll also see the outputs. Oh yeah, and yeah, just for those of you who are want to know a little bit more about this particular demonstration. Oh yeah, anyways, there we go. So we have something called a loss function, which measures the error on our particular neural network, and over here as you can see the loss is going down. There's essentially this algorithm called gradient descent, which is used to reduce the error of your neural networks. And finally we evaluate our neural network and see that we have 98% accuracy. This is quite common in the MNIST data set. It's a solved problem and it's quite easy. Yeah, and over here this last bit over here is executing a little bit on the test data set, and as you can see we have the images over here, and our model is able to correctly classify these particular images as handwritten digits. For example, you can see over here there's a picture of a 0 and the model predicts 0. So yeah, that was a little bit on Power AI and convolutional neural networks, but deep learning is much more than that. We have very interesting algorithms and research being done right now in deep learning. A particularly interesting example that I found recently was the deepfakes algorithm. What this algorithm does is it swaps out a person's face from a video with another person's face. So this is commonly used like right now in applications where let's say swapping out an actor, a face of an actor in a movie with your favorite actor. So people have done this algorithm and they've gotten quite reasonable results, and you can find many more examples online of the deepfakes algorithm. But one particularly lucrative application that I found for this was in computer graphics. So over here we have a few images from a game called FIFA 18, which is a soccer game, and over here so what we're doing over here is swapping between the two faces, cycling before. So the image that looks less professional is actually the computer generated imagery that's used in this particular game. But what the author of a blog post that I read recently, what he did was he used the deepfakes algorithm and he trained it on real images of these particular soccer players, and what he was able to do is actually considerably improve the quality of the computer generated graphics. I find this particularly interesting application of this particular algorithm, as it can provide huge improvements in animation and game design industries. Another interesting research paper that was done recently was the dense pose algorithm, which was created by a team of researchers within the Facebook AI research team. And it's quite self-explanatory through the video, but what you're essentially doing is mapping out the individual pixel values of a human in a particular video, and you create UV surface coordinates of these people. And what you can also do is once you've created the mapping of the human body based on a pure video, you can actually swap these out for interesting, like you could probably like add a a hat or something. And this is a little bit more the details on how exactly the dense pose system works, but we're not going to focus on that today. So what's next for AI and deep learning? So as of now, many people believe that computer vision is a solved problem. This is because computer vision involves static data. The images are of a fixed size in most cases, and even if the images are not of a fixed size, we can pad the images and make every image out there of a standard format, a standard size of a matrix. And currently we have incredible algorithms out there for computer vision, and we've seen greater than human level performance on some of these image data sets. And an example would be ImageNet, where essentially it is a group of a lot of images encapsulating 1,000 different categories like airplanes, buses, ships, etc. And we've achieved greater than human level performance using deep learning on this particular data set. So there's a lot of research being done now on sequence models, particularly sequence to sequence models and generative networks. So far we've talked about how deep learning can be used to scan images or go through data and perform regression, classification, all that kind of stuff. But deep learning is much more than that. People have also created algorithms that's able to generate new data, not only analyze it. And the goal is eventually to come to a stage where all of these tasks, speech recognition, image classification, machine translation, all of these tasks should be, using the help of deep learning, should be able to be optimized to a state where they're able to surpass human level performance.
So in a recent experiment conducted, a group of researchers wanted to train an AI machine system to classify or identify between dogs and wolves. And as they did, and when they were testing the machine, when they gave the machine a picture of a dog, the system classified it as a wolf. The researchers were baffled. They didn't know what happened, what went wrong. So they dug deep, and when they went to when they identified the problem, it was nothing but there was bias when they fed the data set to the system. Every image of a wolf had snow in the background. So the AI system matched the presence of snow to the presence of the animal in the image being a wolf. So
what this essentially shows us is that while we're able to create interesting algorithms that are able to very efficiently scan through data, in the end with deep learning we still don't know why exactly these algorithms work. So there's also a lot of recent research being done on data visualization, and to visualize somehow what deep neural networks are actually doing when we are training them, so that we can better understand what makes these algorithms tick. So another particularly an area of concern would be whether AI is safe right now. So many people like Elon Musk have publicly said that AI is quite dangerous, and we need to be selective in how we go forward in developing them. An example of that would be, for example, this dog or wolf classifier. This may seem like a small or a trivial example, but once deep learning gets implemented at a larger scale and is increasingly used for more and more important tasks, this would be an interesting thing to consider, whether the AI we're developing is safe or not. So anyways, these are the few things we wanted to share with you today, and thank you. Are there any questions? Either anything regarding anything that we talked about, or probably something else related to deep learning? and this is regarding the convolutional, the MNIST example, right? Okay, so the MNIST example that we ran, we actually got access to the Nimbix cloud service, and from there we were able to launch a service which essentially gives you a Jupyter notebook to work on. I don't remember the specifics of which instance we created. If I remember correctly, it was an NVIDIA K80 GPU, and the demo which we showed is actually running in real time, so it wasn't a sped up demo or anything. So we actually completed the entire Jupyter notebook in less than 2 minutes when running it, and we got the Jupyter notebook out of GitHub, so it was part of the TensorFlow Examples repository. And the data set is the traditional MNIST data set. It's a publicly available data set of handwritten digits, each with a particular label on what the number is. This particular data set that we used had 60,000 examples. Yeah, Power AI was already installed as part of the Jupyter notebook. So once you launch the instance comes with TensorFlow and Power AI installed. There are also some other customizable options where you have other frameworks installed as well. So everything that we learned is purely online, so watching YouTube videos and reading blog posts, etc. But the two main resources would be this YouTube channel, Siraj Raval's YouTube channel. So that's one of my favorite resources out there for deep learning. So he publishes content on a weekly basis for pretty much the latest research papers and the math of AI, all that stuff. And there's also another, the place where I got started was the Coursera deep learning specialization. Any other questions? So the course was a 4-month course, but I think it's possible for most people to go through the course a little bit faster. So I took about I think 3 weeks to learn the basics of deep learning and run a convolutional neural network. Okay, yeah, that should be it. Thank you.